Hi guys, welcome back to YouTube channel Chemistry Live UGPG. So today we'll discuss atomic, ionic and covalent radius. So this will be highly beneficial for BSc Chemistry students under CBCS syllabus. So I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime and help to learn others. So this is the syllabus for Core 1 paper Unit 2, Periodicity of Elements. So let's talk about atomic radii or van der Waals radii first. So van der Waals radius is half of the distance between the nuclei of two non-bonded neighboring atoms of two adjacent molecules in solid state. So this is one molecule and this is another molecule. So and this is the internuclear distance between these two molecules. So if it is distance is 3.60 angstrom, so half of the distance is 1.80 angstrom. So that is called van der Waals radius. So two adjacent non-bonded molecule. So here you can see. The name van der Waals radius is used because the forces existing between the molecules are van der Waals force of attraction. And it is obtained by X-ray study in solid state. So for element hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So these are the van der Waals radius and this is covalent radius. So for hydrogen it is 1.20 van der Waals radius and for covalent radius it is 0.37. Similarly for iodine, van der Waals radius is 2.15 and covalent radius is 1.33. So covalent radius is smaller than van der Waals radius. The reason is that in the formation of a covalent bond, the atoms have to be come closer. And this explains why covalent bonds are much stronger than the van der Waals force. So let's talk about ionic and crystal radii. The ionic radius corresponds to the radius of an ion in a ionic crystal. So ionic radius is defined as the distance from the nucleus of an ion up to which it has influence on its electron charge cloud. So the internuclear distance is measured in an ionic compound by X-ray measurements. So distance is taken as sum of the radii of the two ions involved. So for example, sodium, it will lose one electron giving rise to Na plus cation. So here loss of the electron takes place. So with elimination of one electron from an atom, the number of electrons decreases while the nuclear charge remains same. So the nuclear charge now acts on a lesser number of electrons. So hence effective nuclear charge per electron increases and the electrons are more pulled in towards the nucleus. So this effect tends to decrease the radius of cation. So atomic radius of Na is 1.54 angstrom and ionic radius of Na plus is 0.95 angstrom. Similarly, Cl atom will accept one electron giving rise to Cl minus anion. So here gain of electron takes place. So an anion is formed with an extra electron added. So the same nuclear charge acts on larger number of electrons. So the effective nuclear charge per electron is reduced and electron held less lightly by the nucleus and electron charge cloud expands. So the radius of anion is larger than the corresponding atom. So for example, atomic radius of chlorine is 0.99 angstrom and ionic radius of Cl minus ion, that is 1.81 angstrom. So periodic trends in ionic radii. So the ionic radii increase in moving from top to bottom in any given group and decrease in moving along the period. So if we move along the period, it would decrease and it will increase from moving from top to bottom. So here it is 0.60, for cesium it is 1.67, so for lithium 0.60. So as the atomic size decreases, as we move along a period, so the ionic radius also decreases. Since the atomic size increases as we move down the group, the ionic radius also increases as we move down the group. So here you can see the radius ratio Rc plus divided by Ra minus and their coordination number and their geometry. So this one we have already discussed. So now let's talk about what is covalent radii. So it is defined as half of the distance between the nuclei of a two like atoms bonded together by a single covalent bond and can be determined by X-ray crystallography. So however, the length of a bond between two unlike atoms, that is atoms are differing appreciably in their electronegativity value. So we can find out RAB equal to RA plus RB minus 0.09 whole into chi A minus chi B. So where Ra, Rb are covalent radius of A and B atom and chi A and chi B are electronegativity of atom A and B. So this equation later modified by Porterfield as RAB equal to RA plus RB minus 0.07 whole into chi A minus chi B square, equation number 2. So here the covalent radii value is hydrogen 0.37 and moving down the group cesium 2.25. So down the group it increases, and if we go along the period from left to right, so lithium 1.34, nitrogen 0.75, so it decreases. So the covalent radii decrease in moving from left to right in the period and increase moving down from top to bottom in a group. So similarly, you can see your lithium, beryllium, boron, carbon, nitrogen, their atomic number, lithium 3, nitrogen 7, and Z effective for lithium that is 1.30 and the covalent radius is 1.34 and for nitrogen it is 0.75. So the greater the effective nuclear charge, so the greater would be the nuclear force with which the electron is pulled towards the nucleus, and hence more and more reduction in covalent radii in moving from left to right across the period. In moving down the group, the number of principal cells are added and therefore the size of atom increases. So lithium, sodium, potassium, rubidium, cesium and atomic number 3, and here it is cesium 55. So hence covalent radii of atom increases in moving from top to bottom in a group, and here effective nuclear charge is insignificant. So please subscribe to our channel Chemistry Live UGPG. This is also available in the website www.chemistryliveugpg.com. For class 11th and 12th, this is the channel Foundation Chemistry AV. So this is a simple step towards e-learning making life better. Thank you all for learning.